In this session, we are going to see about a radio wave propagation mechanism which are being employed in millimeter wave communication. Just an overview or outline on millimeter wave communication. These millimeter wave communication, we know it will work on 30 to 300 GHz. The key technologies are employed in 5G and 6G communications. So here we should know the basic propagation characteristics like path loss, line of sight, scattering, reflection, diffraction. And these millimeter wave usually supports ultra high data rates, high wavelength, short pulses or a high frequency and low wavelength. These are the fundamentals of radio wave propagation. So first one is electromagnetic wave transmission. We all know when a wave is propagating from transmitter to receiver, there is always an way of propagation either wired or wireless. Usually in wireless, we'll be employing this electromagnetic wave transmissions. In this electromagnetic wave transmission, if there are some coordinates x, y and z, if a wave is traveling and it is having some electric field, the magnetic field will always propagate in perpendicular direction, and hence the direction of propagation of these waves is usually on perpendicular axis to electric and magnetic field. Let me clearly explain you once again. Electric field will be perpendicular to the magnetic field, and in turn both the fields will be always perpendicular to the direction of propagation. So here the basic fundamental of radio wave propagation is electromagnetic wave transmission. Next one is signal propagation through various different medias. For example, there is many medias of propagation like line of sight, scattering, reflection, refraction and much more things. If this is my transmitter and this is my receiver, no signal will have direct line of sight. If there is a transmitter to receiver propagation without any obstacles or without any interference, then it is called as line of sight, LOS, and all the other transmissions are called as non-line of sight. For example, there may be a tall building or there may be some crossings. So these waves will get scattered or reflected. So if there will be scattering, reflection, diffraction, or some signals may be lost or redundant signal may be present in these propagation mechanisms. So there are different types of propagation mechanisms in these basic propagations. Signal attenuation and distortions are unavoidable scenarios in this millimeter wave propagation. Whenever we are sending a signal, there is no certainty that it has to be reached as such 100% to the receiver. It may be attenuated, distorted, or some noises may be added, some signals may get lost, or various replicas or duplications of signals can be reached the receiver. Once it reaches the receiver has to identify the signal which is most likely to the original signal, and it has to be taken by the receiver. So impact of frequency on propagation also relies here. Frequency plays a major role. There are many millimeter frequency bands available in the spectrum. The major band ranges are 24 to 30 GHz, 37 to 43 GHz, 57 to 71 GHz, 71 to 86 GHz. Apart from these basic bands, many bands will come under millimeter wave communications, but the above bands will be frequently used. And if once all the bands are get congested or all the users occupy these bandwidths, then obviously we may move into different bands, maybe terahertz or some other new technologies. So far we are evolving with these frequency bands 24 to 86 GHz. We are going to allot these frequency bands, and millimeter wave antennas has to be designed based on these frequency bands. These are the basic propagation mechanisms. Reflection, we all know, if there is sender and receiver and if there is any obstruction, the sent waves can be reflected back to the receiver. So this is a formal reflection concept. This is more applicable to the propagation mechanism also. Diffraction, when it is diffraction, it is sender, and if it is receiver, the sending signal may be get lost, or there may be some missed signals and it may reach the receiver. While coming to scattering, between the transmitter and receiver, if any object is present, multiple copies of these signals may be present to the receiver. This is called a scattered signal or missing of the original signal. And refraction, we have already know what is total internal reflection. So, and refraction occurs at different angle than reflection. Sent signal may be refracted to some other media. If this is medium 1 and this is medium 2, the sent signal may be refracted to some other medium, which is also a cause of attenuation or losses. And absorption, the sent signal may be fully absorbed by either ground media or absorbed by obstacles or mountains. These are all the absorbed signals. All these things are losses or causes fading for a signal. So these losses and fading has to be eradicated while propagating your millimeter wave communicated signal. So next important concept is free space path loss. So this free space path loss increases with frequency and it limits the transmission range, and it requires high gain antennas. The antennas may be classified into different varieties like high gain, highly directional, high bandwidth. The antennas which have high radiation pattern or which having high absorption, or the antennas may be highly powerful, or it may be a rectenna. Based on these things, millimeter wave communication usually requires high gain antennas, and it is very important to create a link budget. And millimeter wave propagation usually suffers by these mechanisms or by these atmospheric condition. Oxygen absorption, when we are going for high frequency range around nearing 60 GHz or 80 GHz, the oxygen absorption is near 60 GHz, and water vapor attenuation is also high. Rain fade effects, whenever we are moving to high frequency ranges, all these atmospheric difficulties we have to face, and we have to protect the antennas from corrosion. According to that, the materials or substrates has to be made. So these all depend on weather. And since already we have mentioned in our previous classes, this millimeter wave usually suffers from blockages or penetration issues. So there may be human body blockages when we are using for mobile phone antennas, and building penetration loss may also be high compared to your 4G or 3G communication, and foliage attenuation will also be obviously high. And if we are using indoor, there is heavy risk of reflection because of this short wavelengths, or the input may be pulse, it will be get it reflected before it even receives by the receiver. When we are moving into beamforming and massive MIMO, if we are using MIMO, multiple input multiple antennas or arrays, we are going to use anyhow huge number of antennas instead of single antenna. Why? Because the wavelength is very small, we have to pass these signal to large frequencies. Hence, a single antenna is completely impossible to transmit these short wavelengths. Hence, we will be moving into arrays or MIMO. When we are moving into arrays and MIMO, what next? We have to go through beamforming techniques. It can be directional transmission, improving the direction, highly directional or high gain antennas, and enhancing the signal strength of the antennas so that the signal is not going to occur any fading or losses, and the signal has to be reduced interference or intersymbol interference between the channels because of its reduced wavelength again, and the coverage has to be improved. These are the propagational model for millimeter wave communication: free space model, close-in, that is CI model, floating intercept model, 3GPP channel models. These are the common models employed in millimeter wave communications. And these are the applications and future scopes of millimeter wave communication. This we have been already discussed, like 5G or 6G networks and autonomous vehicle, IoT enabled AI integrated smart systems, smart cities, and your future maybe go towards the terrace communication evolution. Thank you.